A workload is a single piece of software deployed with a particular configuration for a single purpose. It may comprise multiple running instances of software, all of which perform the same task. And these are some of the examples of workloads. For instance, a web server running a Python web application, or an instance of a MySQL database, or a worker program processing items on a queue, or a group of replica pods running in a Kubernetes cluster. A workload identity is a way for a workload to prove who it is, prove its authenticity to other workloads. And these are some of the goals or an aspiration for a workload identity. A workload identity should be issued upon the workload start without having to do anything. It shouldn't have to possess or maintain a secret or password to exchange for an identity. You can think of it like a child when he's born. When he or she is born, by the virtue of being born, a birth certificate is issued to that child. The child doesn't have to apply for an identity or a birth certificate. A workload's identity should be cryptographically verifiable, that is, be unforgeable. And a workload's identity should be short-lived and automatically rotated. And finally, a workload's identity should be portable across processes, machines, clusters, and cloud boundaries. In the old world, where everything was more or less static, IP addresses were a good way of identifying workloads. However, in the new world of microservices, where services are deployed constantly and new versions are deployed, and the IP addresses of the new versions may change from the old one, it's not really a good way of, or actually it's not practical to be tracking workloads through their IP addresses. The other problem is, of course, now we have the clouds, so some of the services might be deployed to the cloud. So when the client from, let's say from our data center calls a service in the cloud, the IP address of the caller or a pod, let's say in our environment, a pod is not really carried to the service because it goes through a NAT address translation because the IP address of the pod is local. So this is another aspect that the workload identity framework that we'll be talking about will try to resolve. So how do we achieve these really lofty goals for workload identities? So that is the topic of today's agenda. We'll introduce you to a specification called Secure Production Identity Framework for Everyone, or SPIFFE. So SPIFFE tries to standardize workload identity and how they are created and managed. We'll also talk about a SPIFFE runtime environment, which is an implementation of SPIFFE specification. It's not the only implementation, but we're going to concentrate in today's agenda on this framework, which is called SPIRE. And we will also do a demo. SPIFFE stands for Secure Production Identity Framework for Everyone. It is a set of open source standards for securely identifying software systems in dynamic and heterogeneous environments. As mentioned, distributed design patterns and practices such as microservices, container orchestrators, and cloud computing have led to production environments that are increasingly dynamic and heterogeneous. And as I mentioned, just relying on IP addresses to identify workloads is no longer practical. Architecturally, SPIFFE is a set of open source specifications for a framework capable of bootstrapping and issuing identity to services across heterogeneous environments and organizational boundaries. At the heart of this specification is the one that defines short-lived cryptographic identity document called SPIDs or SPIDs via a simple API. Workloads can then use these identity documents when authenticating to other workloads, for example, for establishing a TLS connection or by signing and verifying a JWT token. So we'll go over this in more details next. So let's go over the SPIFFE components. The first one is called a trust domain. So a trust domain is basically a security boundary that identifies that the IDs that are created within this environment, this trust domain, will be respected and accepted anywhere within this trust domain. And vice versa, in this environment, there's a different trust domain. All the identities that are created are respected here. It is also possible to set up a trust relationship between the trust domains. For instance, in this case, we have a company called acme.com, which has set up two trust domains, one for the production environment and one for the staging environment. A trust domain is presented by a namespace. So it always starts with SPIFFE -- and the name of the trust domain, like here and here. And as we mentioned earlier, it is a security boundary. And it includes one or more signing authorities. So basically, this signing authorities issue certificates to the workloads. And these certificates become the identity of the workloads that are associated. And then we have workloads, basically any piece of software that is executing, such as a pod or a service, which is maybe outside Kubernetes. It has a SPIFFE ID. And a SPIFFE ID is a string that uniquely and specifically identifies a workload. And the format of the SPIFFE ID is SPIFFE -- and the trust domain / and the name of the workload. The workload also has a SPIFFE verification identity document or SVID. It's basically a X509 certificate that is assigned by and is signed by this authority here. And that is how the workload basically identify itself through this X509 certificate. And the name on the certificate or the alternate name on the certificate is the SPIFFE ID on that certificate. And we mentioned SPIFFE ID is a document which a workload proves its identity to a resource caller. There's also a trust bundle. A trust bundle is a collection of one or more certificate authority root certificates that workloads should consider trustworthy. So in this case, we have this one, of course. This was signed. This is a CA that signed its certificate, so that is trusted. So any workload identity that is signed by this CA is accepted. If we set up a trust relationship between these two, then all the identities, certificates that are assigned by the other CA will also be accepted. And then we have the workload API, whose job is to provide X509 certificates and trust boundaries to the workloads. SPIRE is a production-ready implementation of the SPIFFE APIs that performs node and workload attestations in order to securely issue a SPIDs to the workloads and verify the SPIDs of other workloads based on a predefined set of conditions. So again, SPIRE is just one implementation of SPIFFE, and it exposes two APIs, one for registration, so as workloads come online, they can be registered through this registration API. And Node API is basically the means by which the agent are able to communicate to the SPIRE server. A SPIRE deployment is composed of a SPIRE server and one or more SPIRE agents. A server acts as a signing authority for the identities issued to the set of workloads via agents. It also maintains a registry of workload, identities, and conditions that must be verified in order for those identities to be issued. Agents expose the SPIRE workload API locally to the workloads and must be installed on each node on which a workload is running. So basically, this is the architecture. So we have the SPIRE server. We have one or more agents that constantly communicate with the SPIRE, and as workloads come online, they call into the workload API and request identities, and those requests goes to the SPIRE server. Let's dive deeper into the SPIRE server. So these are some of the components that are used in a SPIRE server. The first one is data store. So server uses a store to query and update various pieces of information such as registration entries, which nodes have attested. So attested means verified, authenticated. What selectors for those nodes are. So select is basically a set of claims or attributes that a node has. Next one is key manager, and it controls how the server stores private keys used to sign X509 SFITs and JWT SFITs. So by the way, I forgot to mention that in addition to X509 certificate, the server or a SPIRE server can also issue JWT tokens. And by default, it's in memory, but it can be changed. You can specify a different store. So node attester. So again, before, when the nodes come online for the first time, a node, what do we mean by node? So wherever that workload is running on, first the node itself that is running on. For instance, if it's in Kubernetes, then a Kubernetes worker node would be the node that needs to attest or authenticate itself or prove its identity. And then, so there are various ways that the nodes that when they come online, they can verify themselves depending on where they are. For instance, if they are in EC2, like there's a VM, if this is a VM running on AWS, then it can present its EC2 instance on AWS using EC2 instance identity document. So this is basically an identity that AWS has issued to that VM. And that VM presents this to the node attester, to a SPIRE server. And a node attester then connects to or contacts AWS and says, hey, this guy is saying that it belongs to you, and this is his credential or his identity. Is that true or not? If it's true, then that node becomes attested because it was verified by AWS that it's indeed the identity is correct. Or the VM could be a Microsoft Azure, and in that case uses Azure Managed Service Identifier or identities. Or if it's on GCE or in Google, then it presents itself with it can present itself with a GCE instance on Google Cloud using GCE instance identity token. So all of this, again, they say this is who I am. And in any of this situation, then the attester, node attester, will contact one of the wherever the node is coming from and verifies that the node is actually is what is claiming to be. As you can see, there is no user ID and password. There is no initial certificate. So this is how the attestation or verification is done, which is really cool. Or if it's in a Kubernetes node, a worker node, then it connects through to Kubernetes through kubelet and verifies the token, access token, service access token that is associated with that node. And if it's running a server that doesn't really belong to any of these situations, then it uses TMP, which stands for Trusted Platform Module. So basically, this is a module which is burned into a chip by the manufacturer, and it has a certificate that specifies the name of the server, and this is how the server then can verify itself to Aspire. A node resolver is basically, it helps with the node attester. So it provides a little more information or about the node, and there are a number of node resolvers. One is EC2 for AWS and Microsoft Azure. So basically, they provide more attributes about the node. But the heavy lifting is really done by node attester. This is kind of more information about the node. So by default, the Aspire server itself is a CA certificate, that is, issues self-signed certificate. However, if you have a CA certificate issuer in the environment that is installed, then we can specify that don't use your own CA, and then we can point to wherever the other certificate external server is, and Aspire will use that to issue certificates for the workload. So let's take a look at SPIRE Agent and the components that are installed on it. The first one is Key Manager. The agent uses this storage to generate and use private keys for X509 SFITs issued to workloads. So as workloads are created, then the agent on their behalf will be requesting a certificate or for their identity, and that X509, the agent will need to create a private key first and then make a request for the certificate. So where that private key goes by default is memory, but again, that can be changed. So this plugin basically helps in where the storage should be. And like the Aspire server, the node attesters on the Aspire agent also collaborate with Aspire agent in order to attest the nodes that they're running on. And again, it's the same one that we discussed earlier. Also, the workloads, when they come online and request identity, they need to be validated. And there are a number of ways, kind of similar to node attester. There are different attesters for workloads such as Kubernetes, Docker, and Unix. Basically, if there's nothing else, then if you're like this is a standalone machine, you need to be attested. So again, remember, these identities are issued not just to Kubernetes, but to any server running anywhere. So those can be, the identities can be generated for those. So these are some of the workload attesters that come with SPIRE Server. So as we've seen so far, SPIFFE and SPIRE can be used to provide strong identities in many environments. It's not just limited to Kubernetes. Kubernetes is just one environment. So in this talk, we're going to concentrate on Kubernetes and how it's integrated with SPIFFE and how SPIFFE provides identity for pods. So maybe there are a couple of scenarios in which this can be implemented. One is by service mesh providers, such as Cilium and Istio, and they can use Istio and SPIFFE to create workload identity or for the pods. So workloads in this case would be pods. So they can create strong identities for pods, and those identities can be used by pods to set up mutual authentication and also access control. The other option would be by large organizations to set up their own set up and manage their own SPIFFE environment the way they want to. So in any case, there are some parts such as a workload orchestrated that needs to be implemented by whoever does the implementation. So this is not really meant for individual users. If you're either you can consume the finished product through service provider, or if you are a large organization and you have the expertise to implement your own. In any case, we go through the process of how that is done. Let's say we deploy SPIRE Server. We install it in the Kubernetes environment. We'll go through the process of deployment and how we can deploy that in our environment and during the demo. But let's say we deploy the SPIRE Server, and SPIRE Server is actually deployed as a pod itself. So the first thing that SPIRE Server does when it starts is check to see if any upstream CA has been set up to use. So if you recall, SPIRE Server comes bundled with its own CA, or certificate authority, for signing certificates for identities. Let's say in our case, we will be relying on this CA, the built-in CA, so this will be our signing CA. And then next, it will create a trust bundle. So a trust bundle, again, is a collection of the security domains that it trusts. So obviously, it trusts itself, and if we set up trust relationship with other SPIFFE environment, those will be included here. So basically, these are public certificates that we can get from other environment as well. And this will be sent to the agents and also to workloads, and workloads can use this bundle to see when they're doing mutual authentication, and when they receive the identity of the other pod, and they can validate that pod is legit. And the way they do is they use one of the certificates to see if is signed, the other pod identity is signed by one of these certificates. So that bundle, trust bundle, then is saved inside a database. At this point now, the Node API and registration API comes online, and they are ready to be used or be called by clients. At some point, the SPIRE agents come online. So on each Kubernetes node that we have, a SPIRE agent will be installed, and every agent will be managing all the pods that are created on that node. Next, the API, the SPIRE agent calls the SPIRE server to the Node API, and then it gets the trust bundle that was created earlier in the SPIRE server. The next step is for this the agent to actually attest or verify the identity of this Kubernetes node. So it goes through the node attester. In this case, will be the Kubernetes node attester, and then what it does, it gets the service account token that is assigned. Basically, the service account is assigned to this node, and that token is signed by Kubernetes itself. So it gets that, send it through the API node, and then the SPIRE server sends that service account through its own attester to Kubernetes and says, hey, we have this node, it is claiming that it is in your cluster. Can you verify that? And this is the service account token. And Kubernetes then will validate that because it has signed, if it has signed this service account token, then it says, okay, yes, it's been signed by me, and that belongs to this cluster. Then, in that case, then SPIRE server creates a SPI ID, or basically an identity for the agent itself. Now, every time that agents will be connecting to the SPIRE server, will present this SPIFFE ID as identity, as the proof of its identity. So again, as you can see, there is no service account, there's no user ID, there's no password, there's nothing, there's no initial certificate. So everything is really happening dynamically. And this is one great reason why SPIFFE ID is very popular. And then at some point, it calls into the Node API and basically asks, are there any workloads assigned to me? And so far, there's nothing yet. So in this case, no. Let's say now we are going to deploy an application. A pod is going to be deployed. So this is the command that is sent to the Kubernetes. It goes to the API server, goes to the kubelet, then goes to CRI or container runtime environment, and then calls into the container runtime to actually create the pod. In the meantime, the workload orchestrator gathers information about the pod that's being created and sends a request, basically creates some information about the pod. And this is the format. These two are mandatory, so SPIFFE ID, so it needs to generate a SPIFFE ID based information that it's got so far. So, and the format is SPIFFE, SPIFFE and then colon / and the domain name, the trust domain name, in this case, let's say we call it mycompany.com / and then we, based on the implementation of this workload, can use anything to describe what the workload is. In this case, we're going to use the name, for instance, we're going to use the name of the pod that is being created, which is a service called orders. We also it needs to specify the parent ID. So that is basically what agent will be managing this. And since this was created on this node, so this SPIRE agent would be the one that will be specified here. And then it can generate a number of metadata called selector. So this basically to better identify this container or this pod. And it can be anything. Again, it depends on the implementation of this orchestrator. So in this case, let's say we use the name. So we add the name of the pod, which is orders, as one of the selector. And the other selector, let's say we're going to use what namespace that is being created in. And then it sends the request to the API registration, and then now this pod is registered. So eventually that pod is created here. And so that now that we have this workload is registered in the database. Then later on, the agent contacts the SPIRE server to say, has any workload been assigned to me? And in this case, yes. So it updates its own records. Now it has a workload called orders that will be managed by it. So next step is for either for the pod, either itself or an agent on its behalf, and helper on its behalf will be calling into workload API and say, I need an identity. So because this pod is already will be managed by this agent, so this agent knows the information, already got the information about it. So it can then validate the information that is claimed to be. So the next thing that it needs to do is it needs to go call the workload attester and gets the information about this pod, for instance, the process ID, the pod name, and so on, and sends this information through kubelet to the control plane and gets some information about the pod. And again, this will be similar to what was created as registration. So the purpose of this is to validate that this pod is actually claimed, it is managed, it's the pod that it needs to manage, and information is correct. So it checks the compares information that it received from the SPIRE server and the one that it received from the control plane and SPIRE server, and to see if they match. If they do, then it will request SPIFFE ID or identity for the pod. So it gets the SPIFFE ID or the identity along with the trust bundle and send them to the pod. Now the pod has the identity. Its identity is signed by the CA here, and also it has a bundle, trust bundle. And so it can now participate in mutual authentication. And note that these identities are very short-lived. The certificates expire very quickly. And then behind the scene, the SPIRE agent will be requesting new certificates for all the workload that it manages. So this is a great security feature because it's very difficult to spoof the certificate. They're very short-lived. So this is really a quick view of how Kubernetes is integrated with SPIFFE and SPIRE Server. So next we are going to kind of walk through this process a little bit and manually registering workloads. And again, this is not really done by individual. Either the service mesh providers or larger organization can implement their own SPIFFE environment. But just to know, kind of a little bit, be familiar with some of the APIs involved here, we're going through that process. It is really optional for you. In the next demo, or in the next video, we're going to look at how Cilium implements and integrates with SPIFFE ID and how IDs are created in Cilium. Before installing SPIRE in Kubernetes, there's a requirement, basically a prerequisite that needs to be met, and that is we need to set up a default dynamic storage class and its associate provisioner. So storage classes are used by pods, containers when they are deployed. If they need storage, we need to some way of providing that storage to them. So the storage classes is the way that we provide storage for the pods so they can mount it and use it. For instance, if you're deploying a container that is a database, then obviously the database needs storage, so you need to provision that for it. A dynamic storage does that automatically, and the default means that we define a storage class that anybody can use, any pod, as long as they need the storage, they can specify that storage class, and then it automatically does the provision for them. This dynamic storage class is, well beyond this video, but I have another video that I go into deep discussion on that, and I put the link up here in this corner so you can watch that if you want. So assuming that if you are in Kubernetes, log in Kubernetes master, you need to first define where your storage is. So either in your, if you're learning, maybe we can use your Kubernetes environment itself, like the master. If you're logged into the master, you can then do the following steps on it. Or if you have a different server, then you can, on line 6, you can SSH to whatever service that you have, Linux server. And then you need to install the NFS-kernel server. So in order to creating, share, and export those shares, basically, we need to install the NFS server, and this is how we install that. And the next is we need to create a folder or folders that we want to share. And on line 13 or 14, first of all, we create a directory, and typically it goes under /export on Linux. And then I first specify volumes. I create a folder called volumes, and then I create a subdirectory under that called dynamic. So you don't have to do that. You can just create a folder called dynamic or volumes under the export. So in the case that you also want to create static provisioning, then under volumes you can have another subfolder called static. But it's really up to you. And then once you create those, you need now to export or share those out. And so this is on line 18. this is the command that we use in Linux to export or share that folder. And then once you do that, then we exit, and then we need to then restart the NFS kernel server, as the command says here. And then once we do that, then we are done as far as creating a share on Linux, and then we can exit, assuming that you did that on a different server, on your storage server, then you can then exit. And then you, on the Linux side, on the Kubernetes side, if you want to test this, you want to make sure that you can actually access the share before installing the provisioner. It's advised actually to do that. So install NFS on the server side, and this is the NFS-common. This is what you need to install in order to access the shares that are created or exported by NFS. So you install that, and then we can then mount the volume, and then you specify. This is 192.168.0.14. This is my storage server, but change the IP address as needed, and then we do that, and then I put the password, and then we can then mount to do a test, 27 mount /grep NFS, and we can see now that it shows the NFS, the export that we did in the previous step, so it shows up here. So now we can successfully access the share or export that we created. And then on line 28, we can unmount if we don't need that anymore. That was just for testing. Now the next step is to actually create a provisioner. And for development, I would recommend install the NFS provisioner. It's easier to manage. So on line 32, we can use Helm to install NFS subdirectory external provisioner, and this is where you get it from. And then once you add that to Helm, then you can run this command on line 33 to install the NFS provisioner, and then you specify the NFS server that you set up, and then just make sure you change your IP address to whatever your IP address is, and then the path to the directory that you exported. And then, so that's it. Then the provisioner is installed. Now if you need to later on uninstall it, this is how you uninstall the provisioner. And then on line 41, we can verify, once you run that, hopefully everything is installed correctly. And then on line 41, we can test our deployment. We'll see that this is what it does. It create a deployment called NFS-subdir-external-provisioner, and then we'll see that it's up to date and available. And then we can take a look at the pods also that was created here, and we see that this is the pod that is created, so as part of that. So provisioner itself is actually installed as a pod. Also to check the storage class that it created on line 45, kubectl get storage class. If we run this, you'll see that the name of the storage is NFS-client. So, and then if we want to, this step, the next step is actually important. We need to set this as the default provisioner, because that's what SPIRE will expect this to see default provisioner. So this is how we do that on line 48. So when you run this command, it will set NFS client that we just set up as the default provisioner. So remember that SPIRE will create a database, as we just talked about it with earlier. So we need to it needs to be able to set up storage, and this is how we kind of set up the stage for it to, when we go to the next step, which is to create install the SPIRE server, then it can use this storage class and the provision that we just installed to actually create the database that it needs. Okay, now that we set up the required prerequisite, let's go ahead now and take a look at how we can set up SPIRE in our environment. So line 1, this is the link to the repo, SPIRE repository that you can download the tutorial that we go through here. You can download that. And then you need to go to that directory, and specifically you need to go to /ks/quickstart. So that's all the files that we are going through reside there. The first thing that we need to do is we need to create a namespace called SPIRE. So kubectl apply -f, and that YAML has the logic to create a namespace. And then we can then verify that on line 8, kubectl get namespaces. And this will create a SPIRE namespace that is listed here. Okay, and the first section that we're going to go through from here is we will set up the SPIRE server itself. And then in the next section is we set up the agents, the SPIRE agent. And in the final section, we look at how we register the nodes and workloads, and then we do a test from a client, a pod that to ensure that you can communicate with this SPIRE agent. Let's go through that then. So the first thing that we need to do is these will create a service account because SPIRE will be interacting with Kubernetes, so it requires a service account that has appropriate permissions. So all this will create a service account and gives RBAC permissions to that service account. And then over here, the next section, we are going to deploy the SPIRE server. So once we run this, it will create a stateful called SPIRE-server, and it will also create a SPIRE server. So that was a stateful that's used for database, and then it will also create a pod for a SPIRE server. It's called SPIRE-server-0. So let's go ahead and run those. And then we can verify that on line 23. kubectl gets stateful, and then in the namespace is in -SPIRE. So we'll see that SPIRE server is created, is not ready yet, so we need to make sure that it's ready. Let's go ahead and run that. Now we'll see that it's ready, in ready state. So let me clear that. And then we can also then on line 24, kubectl get pods. So that was a stateful. This is now the SPIRE server itself. So let's go ahead and run that, and we'll see that this is the name of the pod that contains the SPIRE server. Okay, now that we set up the servers, now we need to set up the agents. And for agent, again, we need to, first of all, create a service account and give permission, appropriate permission to that service account. So on line 30, these YAML files, you can go through them if you want to, but this is basically what it does. So it will create the binding, the service account, and also the RBAC permission. And then on line 36, now we can install the agent and the agent pod. Let's go ahead and run that. And then we can verify that. So this will be a daemon set. So kubectl get daemon set. So those will be installed on all Kubernetes workload that you have. And in this case, you only have one, so it's just one here. Okay, now the section we need to register workload, but before doing any workload testing, we need to actually register the node. So on line 50, kubectl exec. So we need to exec into the SPIRE server-0 that we installed earlier. We need to exec into that, and from this location here, we need to run this create And these are the switches or options. So remember that anything that other registration has to be specified as specific. First of all, we need to create a specific ID. And the format, if you recall, is SPIFFE, then colon, dash, dash, and the name that we give it. So this is for the agent. So we call it SPIRE Agent. And then next one is we add some selectors. So these are, again, these things that can be, other things can be added, but for this one, we are going to add like the cluster, demo cluster, the cluster name, and the agent, and the name for it, and also the service account. And then we need to specify dash node. So this is a node that we are deploying or we are defining. So let's go ahead and do that. And we'll see that the result, it created an entry ID in the SPIRE. And then this is the SPIFFE ID and the parent ID, which is the server itself. And now we simulate situations where now a pod has been created and now it needs to be registered. So the kubectl exec, we need again to exec into the SPIRE server and run this command. So dash SPIFFE ID, we give you the name for it. So, and then again we add a selector, and also we specify the ID for it. So selector would be the namespace and the service account for that namespace, which is default and default. So let's go with that. Now we have defined a workload registration. Now we can deploy now an application that is associated with that registration that will be kind of tied up to that deployment. And then we can now exec into that application we just deployed. We go inside to that pod. So kubectl exec -it. And this is basically to get the name of, this is a label that this will create for that client called app equal to client. And then from there, we're going to basically call into the SPIRE agent. Let's go ahead and run that, and it will show us all the registration that it has so far. So this was a quick overview of SPIRE and how do we can set it up inside Kubernetes environment. And again, remember, SPIRE is not, and SPIFFE are not limited to Kubernetes, but this is just a use case for it. And also remember that an end user usually, is not going through this process. It's really used mostly by tool makers and large organizations. Tool makers such as service provider, for example, Cilium and Istio, they already take advantage of SPIFFE IDs and SPIRE to create workload identity for their pods, and those pods can participate in mutual authentication. Also, Cert Manager has created a plugin that uses it doesn't use a SPIRE agent, but it uses SPIFFE ID, like the specification, in order to provide inter-cloud workload registration so that workloads from one cloud can be accessing resources from resources in other clouds, for instance. And also some databases such as Postgres, also they've started to include or support workload identity. So rather than having user ID and password, those workload IDs will be respected as the user and will be authenticated. So that said, SPIFFE is really still a work in progress, but I see that in the future, I would imagine it will fulfill all the goals and aspirations that we talked about at the beginning of this video. I think eventually will be fulfilled, and I think it's in the right track. So I hope you enjoyed this video. In the next video, we're going to see how Cilium takes advantage of SPIFFE ID and SPIRE. Hope you can join me.